All right. Well, happy Monday. This is week 7. So this means this is like the week after this week, we're halfway done. So it should be fun. What we're going to be doing this week, just to kind of keep you all on board. So there are going to be 2 homework assignments due on Friday. One is the one that was assigned last week that hopefully you've had a chance to at least get started on. The next one is posted on Moodle now. We'll be able to do part of it after today and maybe part of it after Wednesday. Finish the rest of it after Wednesday. It's pretty short though. I made it like a 10-point homework assignment. It is, yeah, it's fairly short. It shouldn't take you too long to actually get through that. And then I'm trying to think if there's anything else. That's the other thing that's coming up relatively soon is our next exam. It's a week from Wednesday. So we'll talk more about it later, but just that is coming up. It'll be on primarily like chapter 4 stuff, but then also some from the stuff that we're doing this week. So yeah, I think that's all the announcement-y stuff. If you are having problems with some of the, especially like the last homework assignment, homework 5, is that right? If you're having issues with that or how to think about those, right, this is a good time to shoot an email to me and try to meet up, or right, I don't have set office hours, but I'm happy to meet you guys either like virtually or in the study room or something like that. So feel free to contact me and we can set something up if that's something that would be helpful. Yeah, I don't think other than that, fairly normal week for this week. So what we're doing today, we kind of finished last time, and I want to kind of briefly review what we were trying to do before we dive back into some of the math of it. We were looking at really trying to describe flow by looking. So we had something, and again, you should have this already in your notes, but if you just look back at what you wrote from Friday, we said we can look at flow by defining a really small control volume. So we define a little box. This is our control volume. It's a control volume in a larger flow. So fluid is moving, and this is just a little section of the world that we're looking at. This is our control volume. We can give it a size dx, dy, dz. Right, we're going to shrink things down until it's a differentially small control volume. And we're going to use this for our differential CV and Reynolds transport. To look at flow. So there are going to be 2 aspects of this. Right, we're trying to understand how fluids move. So there are going to be 2 aspects of this. The first is conservation of mass. The second is F equals ma. So those are going to be the main 2 things that are going to dictate how fluids actually move and behave. Those 2 things happening together. I mean, right? So the fluid will have to obey conservation of mass, and it will have to obey F equals ma. It has to do those 2 things simultaneously. So that's really what we're looking at. We're trying to take both of these physical laws and apply them now to these differentially small little particle or little areas of space to be able to look at fluid flow. So our, where we left off last time was looking at flow in the, in just the X dimension, or just the X direction. Right, we said we don't need to care about all of the directions all at once. Let's just look at the X direction. And we could look at the flow into and out of the YZ plane. So we had two planes like this. This would be dy, dz. And we could look at the flow into that plane and then out of our second plane over here. Okay, we said the fluid is going to flow in with, not y, it's going to flow in with some velocity, ux, and it will have a density rho x at this point. So this would be on our x-axis, this would be point x, this would be x plus dx, right? Because that's the other side of our cube, dx away. And it's leaving here x plus dx and rho x plus dx, whatever happens to be coming out. So hopefully this is all just kind of refresher from what you have in your notes so far. Okay, so what we wanted to do was then to look at Reynolds transport theorem in this kind of context. So our Reynolds transport theorem, the continuity equation, for a control volume is this. Integral, I guess this would be d dt of rho d volume plus the integral over the control surfaces of rho v dot d a. Okay, if we have uniform velocity, then that second term just becomes a sum instead of an integral. That's a reasonable assumption to make because, right, we shrunk things down so that they're super duper duper small. And if you make something small enough, right, then the velocity, even if it's changing, it's still going to be uniform over that really, really tiny area. So this works because dy and dv are really, really small. Then we would get that 0 equals ddt rho dv plus, now this would be, we look at the fluid coming into the left side. So this would be rho x times negative ux a. That would be what's coming into the left-hand side. You get a negative because the area, the velocity is coming in from the left and the area is pointing outward. So that would flip the sign. Plus rho x plus dx times u x plus dx times a. Right, fairly straightforward, like we've done a whole bunch of times now. Now the challenge is getting this from this kind of a notation into a differential equation type notation. So that's where we spent a little bit of time and kind of where we ended last time. So we said this first term, and we kind of split it up. So we first looked at this term, and then we looked at this second part. So the first term was rho v. We said that equals just how the density is changing. So density times volume. So this would be d rho dt dx dy dz, right? How the density changes with time times the volume, because our control volume is not changing size with time. Then the second term here, this is where we have to start kind of breaking down this top equation. So we have rho x, we'll leave that as just rho x. We'll leave ux equals ux. But then we had this kind of weird notation. So the density coming out is equal to the density coming in plus d rho, right? That makes sense. So the density that's coming out equals what came in plus however much it changed. But then we wrote that as this weird, this kind of weird way. So we wrote it as partial rho partial x times dx. And we did the same thing with, so ux plus dx is ux plus du. So the velocity leaving is what it came in plus however much it changed. And then we wrote it in this weird way, plus du dx times dx. Okay, so both of those, they're kind of strange ways to write things. You can see though that like those two things are equivalent because you could imagine like the dx's canceling each other out. Like we have a dx on top and a dx on the bottom. Those would just cancel each other out. Another way of thinking about that is, okay, so the velocity coming in is equal to how fast the velocity is changing in x times like the distance over which it changed. Again, which is exactly the same thing as saying how much, like what came in plus however much it changed. So kind of a weird way to write it, but it makes our lives easier when we start smashing things together. So let's do that. So let's smash really all of these things into this equation that I labeled 2. It's the last thing that we need to define is what our area is. This is the area of kind of these two squares that I've drawn. So the area is dy times dz. So that's our area. dy dz. So let's start smashing things together. So that gives us, well, this first part is going to be minus rho x ux dy dz. So that's the first part. It basically stays the same. And then the second part is going to get a little bit funky. So that will be rho x plus d rho dx times dx times ux plus du dx times dx. So that's rho x plus dx, ux plus dx. times dy dz times the area. Okay. So then we have to actually go through and, right, kind of multiply this guy out. So we're going to have to multiply this out, multiply this through, multiply that through. So what we'll end up with is this big long mess. So this will be minus rho x ux dy dz plus, and it's going to be a whole big mess. So we're going to get everything is, as we multiply this through, it's all going to have a dy dz. So I'll leave that at the end. But we're going to have rho x ux, right, if we multiply the first two terms, plus rho x du dx times dx. Then if we do, okay, the next terms plus ux d rho dx times dx plus, now we take the differential. So this will be d rho dx times dx, well, du dx dx squared. And that will all be times dy dz. So now there are a couple ways that we can simplify things. So the first thing that we can notice is that this term is really, really small, right? Because it has a dx squared. So that dx squared, you take a number that's infinitesimally small, dx, and then you square it, and you get something that's even smaller than infinitesimal. So this goes to 0 because of the dx squared. That's just really small, so we can neglect that. Okay, that's basically 0. The second thing that you might notice is that we have here a minus rho x ux dy dz, and here we have a rho x, positive rho x ux dy dz. So these two terms will cancel each other out. And what we're left with is rho x du dx plus ux d rho dx times dx dy dz. Well, okay. If we look at that, and if you think back to some of your calculus rules, right, you can say, well, that's actually just a chain ruled form of d u rho dx. Dx, dy, dz, right? If you have the differential of the product, you get like the first term times the differential of the second term plus the second term times the differential of the first term, right? Okay, so this is why we wrote it in that weird goofy notation, because it ends up working out fairly nicely down here. So let's smash these things together all back into this top equation here. So we need to take this equation and smash, okay, so we have this term for part 1, And then we have this term for part 2. So we're putting it all together. We have 0 equals d rho dt dx dy dz plus d product velocity times density dx times dx dy dz. And you'll notice, of course, that both terms have a dx dy dz in them. So the dx dy dz, this whole part will drop out of both terms. And we get, as a final solution, 0 equals d rho dt plus d u rho dx. Now repeat for y and z. Right, that was just the x direction. Now we do the same thing, but with the y and the z direction. So we go back to our little cube. Right, we zoom back up here. We go back to our little cube, do the exact same thing, but now we're looking at the flow like, you know, in the other two directions. But the nice thing is, right, all of the math that we just did, it's all exactly the same, and we can just look at it and say, what would the answer be? Instead of, you know, basically instead of where we would have x, we would put a y and then a y plus dy. Instead of u, which is our x component, we would have little v, which is the y component of the velocity. But all of this stuff would just translate like directly from how we handled x to how we would handle y to how we would handle z. So we can just write the final answer. So we would get zero equals d rho dt plus d u rho dx plus d, this would be little v rho dy plus d w rho dz. So this guy is the continuity equation for a differential control volume. So, right, it kind of sets, and think about it, this sets bounds on what a velocity field might look like without violating without breaking conservation of mass. So we are not able to have a velocity field that doesn't obey this differential equation, because that would break conservation of mass. A special case that we often run into is would be incompressible flow. Incompressible meaning that the density is a constant. So if density is a constant, we go back up to our differential equation, density pops out of all of those integrals. And how is the density changing with time? Well, it's not. Density is a constant. So it pops out of the three space integrals, and the d rho dt part cancels out, or that's zero because density is not changing with time because it's constant, not changing with anything. So then we would get 0 equals du dx plus dv dy plus dw dz. Okay. We often can write we can simplify this instead of writing it like this. A common notation that you might see would be 0 equals the gradient of the velocity, where this is dx I hat, so gradient dotted with the velocity, dy j hat plus d k hat. Right, this is supposed to be just an upside down triangle. So that's a notation that just simplifies it. Rather than having to write all of those different integrals, you could write just this, right? That ends up being the same thing. We'll use the gradient operator when we get even uglier equations than this. That's just a way to simplify what we have to write. So it places bounds on fluid flow. You can't flow in a way that would violate conservation of mass. So let's see a little bit how that would work. So let's look at an example. If we have a velocity field which is characterized by this, v equals 2x I hat plus v j hat. We can ask ourselves, so v is an unknown. We don't know what the y velocity is. We could ask what values can the y velocity, or little v, take? So is there an unlimited number of possibilities for that, or only a certain amount? So it has to, our velocity field has to obey conservation of mass. So we'll write first if density equals a constant. If density is not constant, you get more options, but lots of flows are constant density. So if density is constant, then we know that, right, 0 equals gradient of the velocity field. Those two look like the same thing, v vector. Then this tells us that 0 must equal du dx plus dv dy, because we don't have a z direction, so that term is 0 plus. Okay, so du dx is d of 2x. So that equals the just 2. So we have 0 equals 2 plus dv partial v of with respect to y. Okay, and then we just have a really simple differential equation to solve. So we have that, right, we can get everything on one side, so minus 2 equals dv dy, and dv equals minus 2 partial y. So v has to equal minus 2y. And then this is where things can get a little bit funky in these, plus some constant. But it doesn't actually have to be a constant. It just has to be constant in y. So this is our constant of integration, right? And it doesn't actually have to be a constant. It could be a function of x. It just has to be something where when we took the y derivative of it, the y derivative is 0. So it could be x, it could be z, it could be something else. So this gives us, right, the only possible solutions for this value of little v. Right, v has to be minus 2y plus something of x. It couldn't be anything else. Otherwise, we're violating conservation of mass. Right, so v equals, what was it? 2x I hat minus 2y plus f of x j hat. And that's the only possible solution, that we could have. We can also do things like, check a velocity field that we're given and check to see if it violates conservation of mass or not. So let's look at just one more quick example. Check a velocity field to see if it violates conservation of mass or not. So let's say we have a velocity field that's x squared plus 2y plus z squared I hat plus x minus 2y plus z j hat plus negative 2x z plus y squared plus 2 z k hat. So we could look at this, is v incompressible? So we could ask something like this: is it incompressible? Is the density constant? And if so, does it violate conservation of mass or not? So this is really asking, is this equation du dx plus dv v dy plus partial w partial z actually true. So if we wanted to do that, now we can go through and take all of these partial derivatives. So we would take the partial derivative of u with respect to x. So this equals 2x plus 0 plus 0 I hat. Sorry, no, not I hat. Plus, so now the second one, we only care about the y derivative. So that's going to be 0 minus 2 plus 0 plus now the z derivative. So that's minus 2x plus 0 plus 2. And then we can go through and ask ourselves, is this equation true or false? So this would be 0, 2x minus 2 minus 2x plus 2. So we would answer that yes. This is an incompressible flow. This does not violate conservation of mass. Okay. So we can do some of these, obviously, are kind of artificial problems. I mean, you guys can all tell that. What's going to be cool about it is when we take this and apply this in tandem with F equals ma. That's when we're really going to be able to describe fluid flow at a kind of a higher level. But we can do some of these same kind of things. And really all that we're saying is, are these things, do these work with conservation of mass? Okay, the next thing that we'll look at, and this will feel a little bit weird to do the things that we're about to do. It's going to feel like just an exercise in math. It's not just an exercise in math. It will feel that way for a little bit, but what kind of drops out of it is actually a better way to understand some of the visual like flow fields that we've seen. A better way to understand that and how we can understand like streamlines and how those actually relate to things like velocity and flow rate and different things like that. So it's not just a totally math thing, although it will feel weird, at least for the first little bit. So let's set aside for right now conservation of mass and look at something that we'll call the stream function. Okay. So let's look at, instead of a three-dimensional flow, we'll look at a two-dimensional flow. So this is a flow that only, or it would be characterized by the velocity field equals u I hat plus v j hat. It only depends on x and y. So it's pointing in two directions and it's only depending on x and y. We're going to define this weird thing called the stream function. So we'll define the stream function. The stream function is going to be psi, right? Poseidon's favorite variable. We'll use that and we'll give it this weird definition. So we're going to define it so that the partial derivative of the stream function with respect to y is equal to u, and the partial derivative of the stream function with respect to x. So that's defined as, or I guess I'll write it like this, negative v. So we have this super strange definition. So we take something and we're kind of like defining the stream function. We're kind of trying to capture both components of the velocity, both u and v, with this one goofy thing that's defined in terms of partial derivatives. Like I said, this is going to feel weird until like some of the stuff actually drops out. So let's consider, you get an extra page here. Come on, buddy. Okay. So let's look at this kind of in the context of an example. So we're going to look at flow in a corner. This is a velocity field that we've looked at quite a bit. So for flow in a corner, the velocity equals ax minus ax I hat minus a y j hat. So we're defining our stream function so that d psi dx, or sorry, d psi dy is equal to u and minus d psi dx equals v. So d psi dy equals ax. This would give us that, right, so psi must equal ax y plus an unknown function of x. Right, we would separate variables and then integrate. These are partial derivatives, which is why we get the unknown function of x. So the stream function has to be just a single thing. So these are just two different ways of looking at it. So we're defining like a single function. And like I said, this is going to feel a little strange. But our next equation would be negative d psi dx equals negative a y. So this would tell us that the stream function, again, if we separate variables and integrate, this would give us that the stream function equals a xy plus an unknown function of y. Okay. These two things, so psi is a single function. So these two equations must be identical. So we need to basically take these two equations and mash them together in a way that they are exactly identical. The only way to do that would be if that unknown function of, so if, right, so we would get axy plus f of x must equal axy plus f of y. Those two, that has to be true. So right, f of x must equal f of y must equal c, right? Just a regular constant. So we're going to define this weird thing called the stream function. We're going to get to it by doing two different integrals, integrals of partial differential equations. We have to do like these two separate integrals, but then it's one single, like psi is a single thing. So psi equals a xy plus c. Okay. So we're going to get to it by doing these two separate integrals, saying that it's like psi is just a single thing. So we have to, like, these two things have to be giving us the same original function. And then kind of comparing and smashing them together into a single function. This also has to, psi itself can't violate the continuity equation. So this gives us this weird thing called psi. This would tell us that the 2D, this would have to obey the 2D continuity equation. Obey continuity, right? Which would tell us that dx plus dv dy equals 0. So if we would put this in terms of psi, this would be dx of d psi dy minus d psi dx equals 0. Okay. If we did, that would be d squared psi dx dy minus d squared psi dy dx equals 0. So for our example, psi equals a x y plus c. This would give us, so we would take first the x derivative of that and get a y, and then we would take the y derivative of that and get a. Get a, and then we would subtract, okay, do the same thing. First take the y derivative, that would give us ax. Then we would take the x derivative, that would give us a minus a would be equal to 0. So, okay, this checks out. So we did this weird thing where we defined psi. Again, I'm sure that this just feels like some weird thing that I'm doing up here, which is fine. I do that sometimes. We'll come back next time and hopefully be able to see why we actually did this and how it has any use to us. That will be on Wednesday. With some of this though, I think we already have some of the tools to do the first little bit of the next homework assignment. And I think after Wednesday, you'll have enough to do everything, but make sure I would focus on the last homework assignment, make sure that gets done first. Because like I said, this one's going to be kind of short comparatively. All right, I hope you guys all have a good Monday.